Have you ever heard of molecular doppelgangers? I'm talking about chemicals that are built from the exact same atoms, the same parts list, but somehow end up as completely different things. It sounds like something out of science fiction, right? But it's actually a real fundamental puzzle in chemistry, and it explains so much about the world around us. So let's dive in and see if we can unravel it together. To really get what's going on, let's meet two molecules that are having what you might call a major identity crisis. So first up, we've got ethanol. This is a molecule you've probably heard of. It's the kind of alcohol that's in beer, wine, you know the deal. At room temperature, it's a liquid, and it behaves in a very specific, very predictable way. And here's its chemical twin, dimethyl ether. Now, this one, probably not so familiar. It's a gas at room temperature, and it's used as a propellant in things like aerosol sprays. So yeah, you definitely do not want to get these two mixed up. But here's the kicker, the real twist in the story. Even though they have these wildly different personalities, one's a liquid you can drink, the other's an industrial gas, they are built from the exact same atomic recipe. Get this, 2 carbon atoms, 6 hydrogen atoms, and 1 oxygen atom. That's it, for both of them. So, this leads us to the big question, right? How is that even possible? It's like I gave you and a friend the exact same box of Lego bricks, and you build a car while your friend builds a house. How can the same building blocks lead to such different outcomes? Well, the answer lies in this really cool chemical concept, kind of like a secret rulebook for how atoms get put together. And that concept has a name, isomerism. This is the key that's going to unlock this whole mystery for us. Okay, so what is isomerism really? It's the perfect word for what we just saw with our two molecules. It's this phenomenon where compounds share the exact same molecular formula, the same parts list. But because those parts are assembled differently, they end up with totally different properties. And you know, if you break the name down, it makes total sense. It comes from the Greek words iso, which means equal, and meros, which means part. Equal parts. It's just a perfectly simple name for a really powerful idea. Now, this isn't just one big messy group of molecules. Chemists have actually sorted these doppelgangers into 2 major families, and it's all based on how their parts are arranged differently. And here they are. The 2 main branches are structural isomers and stereoisomers. Seriously, once you get the difference between these two, you've pretty much cracked the whole code of isomerism. Let's go back to our Legos because it makes this super clear. Think of structural isomers as using your Legos to build a car versus a house. The bricks are the same, but the way they're connected, the actual blueprint, is totally different. Now, stereoisomers, they're more subtle. This is like using the same blueprint to build 2 cars that are perfect mirror images of each other, a left-handed car and a right-handed car. The parts are connected in the same order, but they're just arranged differently in 3D space. All right, let's start with that first family, the one where the molecules have completely different blueprints. So just to lock this in, for structural isomers, the fundamental connections between the atoms, who's bonded to who, is different. And our old friends from the beginning, ethanol and dimethyl ether, yep, they are a perfect example of structural isomers. Take a look at these 2 molecules here. Both of them have the exact same formula, C5H12. But just look at them. On the left, you've got the 5 carbons all in a nice straight line. On the right, one of them has branched off. Same parts, totally different connection pattern. This specific type is what chemists call chain isomerism. Then you've got something called positional isomerism. In this case, the main carbon skeleton, that ring shape, is identical in both. But see that little functional group, the COOH part? It's just been moved to a different position on the ring. It's a tiny change to the blueprint, but, well, it creates a whole new molecule. Okay, you with me? Let's move on to that second, more subtle family, the stereoisomers. Now remember, with stereoisomers, the connection sequence is exactly the same. The blueprint is identical. The only difference, the only thing, is how they're arranged in 3D space. And this is where things get really, really interesting. So how can you actually tell everything apart when you're looking at 2 molecules? It's actually a pretty simple 3-step process. First, you check the molecular formula. Are the parts lists the same? If yes, move on. Second, you check the connectivity. Are the atoms connected differently? If they are, boom, you've got structural isomers. But if the connectivity is also the same, then you go to step 3. You check the 3D shape. If that's different, you found yourself some stereoisomers. Here, check out this classic example. Look closely. In both of these molecules, the connection pattern is identical. But look at their 3D shape. See how on the left, those two green chlorine atoms are on the same side of the molecule, and then on the right, they're on opposite sides? That one little spatial difference is everything. That's what makes them stereoisomers. Okay, so at this point, you might be thinking, this is kind of cool, but why does this tiny, tiny difference in 3D shape actually matter in the real world? Well, it turns out it matters a whole lot. The bottom line is this. That difference in shape, no matter how small it seems, leads to different physical and chemical properties. And because of that, isomers behave differently out in the world, in our technology, and yeah, even inside our own bodies. So, why is this such a big deal? Well, in medicine, it can literally be the difference between life and death. One isomer of a drug might be a cure, while its mirror image twin could be totally useless or even dangerous. The properties of everyday materials like plastics and fabrics, that's determined by molecular shape. And in our own biology, our sense of taste or hormones, it's all based on a molecular lock and key system. The right shape fits, the wrong one doesn't. In chemistry, shape is everything. And it really leaves you with this incredible thought, right? If just rearranging the same few atoms can create entirely different substances with totally different jobs in the universe, what other amazing secrets are hiding out there? Not in what things are made of, but simply in how they're built.